Okay, so welcome back. So I think I promised one more polar coordinates double integral before moving on to the next thing. So let me dredge up the example that I planned on going over. Okay, so here's a good example just because the region seems really nasty, but it's actually not too bad. So let R be the region to the left. I haven't drawn it yet, so let's go ahead and do that. So let R be the region between the polar graphs of the polar functions r equals theta and r is equal to 2 theta. So what does this look like? Well, I have some inner function. This is the polar function r is equal to theta. Maybe I'll write it here. So r is equal to theta gives me a spiral. R is equal to 2 theta gives me a spiral that is outside that spiral. So this is r is equal to 2 theta. Okay. And so unlike the case of talking about rectangular coordinates and vertically simple or horizontally simple, where we think about a top and bottom function or a left and right function, for polar functions we typically classify them as the inner function and the outer function, right? Because everything is in terms of r and theta, so radius and angular value. And so if I shade the region between these two polar graphs, this is what it looks like. This is my region R. Okay, so i.e. R is the region between the graphs r is equal to theta and r is equal to 2 theta. Can you tell what the angular values of theta are here? So for theta, between what values? So let's see here. I started at theta equals 0. That's my positive x-axis. So I've spiraled around once. So that's 2 pi. But then I spiraled around another half of a full rotation there. So that's an extra pi. So this is theta between 0 and 3 pi. Right, is how we would describe that region. Okay, and so I want to evaluate the double integral over this region R of x squared plus y squared dA. All right, that's the double integral that I want to compute. Okay. So, questions about what I've set up so far? All right, so what do I do when I want to evaluate something like this? So I've already got this nicely expressed in polar coordinates, so I clearly want to use polar coordinates in order to do this. So let's see here, right? My region is described as being between polar graphs of theta and 2 theta for theta values between 0 and 3 pi. And so how do I do this? This would be the integral from 0 to 3 pi of the integral from theta to 2 theta of, tempted to write x squared plus y squared here, but I know that really what I want to do is plug in what x and y are in terms of r and theta. Now, sometimes it helps, rather than trying to do all this algebra underneath the integrand, sometimes it helps to actually separately compute what this expression is in polar coordinates. Or you might just be able to look at that and say, well, I know what that is. I don't have to plug it. Now, let's say that I actually plugged this in. Okay, if I plugged this in, you would note that I would have, so x is equal to r cosine theta, right? So this is r cosine theta squared. That's what, so x squared plus y squared. I'm doing this integrand on the side here. This is r cosine theta squared plus r sine theta squared, which is r squared cosine squared theta plus r squared sine squared theta. I can factor out an r squared, and I have cosine squared theta plus sine squared theta. By the Pythagorean identity, that's just 1, so this is equal to r squared. Now, you can do it that way. There's absolutely nothing wrong with this, but it can save you some time if you just note, well, this is how r is defined anyway, right? So x squared plus y squared is r squared in polar coordinates, and the reason, of course, this is the case is because of this algebra I just did. But however you remember this, you can immediately just say, well, this is r squared here. So actually plugging in r cosine theta and r sine theta, you see that again. So x squared plus y squared is r squared. Now I'm tempted to say this is, dr now, d theta, but that's not quite right, right? What did I not do? So I've not done something. I have screwed something up. All right, intentionally here, but what did I screw up? All right, it's easy to also screw this up unintentionally as well. I'm doing a polar coordinates integral. When I swap, I have this extra r. Yeah, I forgot the extra r. So chat is now saying, yes, I forgot the extra r. So that's exactly what happened here. So x squared plus y squared, that is r squared. But then I have this extra r coming from this definition of how to do the polar coordinates integral. Okay, so then really this is r cubed underneath this. I'm not going to rewrite that. I'm not going to waste a line to rewrite that, but this is really r cubed. And so now I can do this integral with respect to r. So this is the integral from 0 to 3 pi. This is r cubed. What's the integral of r cubed dr? That's 1/4 r to the 4th, right, evaluated from theta to 2 theta d theta. Okay, so I need to do that evaluation. So I'm going to go ahead and bring the 1/4 out. So this is 1/4 times the integral from 0 to 3 pi of, what is this? This is 2 theta to the 4th minus theta to the 4th. Right. So this is the integral from 0 to 3 pi of 2 theta to the 4th is 16 theta to the 4th minus theta to the 4th. So this is 15 theta to the 4th. And so this is, I moved this back inside for no reason. Let's not do that. Let's make this my fraction. So this is 15/4 theta to the 4th d theta. Okay. And so doing the second integral now, this is 15/4 times 1/5 theta to the 5th, evaluated from 0 to 3 pi. Evaluating at 0 yields 0, and so I'm left with 15/4 times 1/5 times 3 pi to the 5th. So let's think about this for a second. This is, so 15 divided by 5 is 3. So then I have 3 to the 5th times 3 times pi to the 5th. So that's 3 to the 6th, pi to the 5th over 4. So that's 3 to the 6th, pi to the 5th over 4. That's good. So I think that's right. 3 to the 6th, what is that? That's like 729. So this is, 729 over 4 times pi to the 5th. Either of these perfectly fine. All right, and so that is indeed our answer. Now remember what this number is actually saying, that this is the volume of the region in space that is bounded above by the graph of x squared plus y squared and bounded below by this region R on the xy plane. Okay, so you might try to visualize that strange looking solid region, but this computes its volume. Okay. So let me know in the chat if you have questions about how that's done. All right. Now, the idea is to take exactly what we did for double integrals and move it up, crank it up one dimension. Okay. And so when we talked about double integrals, we started with a region R that maybe looks something like this if it was pretty nice. So here's my region R in the xy plane. Above this region R, there was a graph of a function in space, so some f of xy. And I wanted to compute the volume of the solid region in space that was bounded above by the graph of that function, below by this region R in the xy plane, and whatever that volume is, it was computed by this thing that I defined, right? This double integral. So this was how it worked. So this double integral was computing a volume of some solid region in space. Okay, and this region, of course, was some solid region. It was bounded above by the graph of function f of xy. So I want to do the same thing for functions of three variables. So the quantity I'm trying to define here is this thing, a triple integral of some function of three variables. So this is the thing that I'm defining. Now, a function of two variables is defined on some two-dimensional region in the xy plane, right? A function of three variables, though, is defined on what kind of region? Well, it's defined on some three-dimensional region D. It's defined on a solid region D in space. Now, for simplicity's sake, we're going to restrict our attention to very special types of domains D. So we're only going to restrict our attention to specific types of solid regions. So we restrict ourselves to a particular type of solid region D. So what particular type of solid region? We're not even going to have a name for it because these are the only types of regions we're going to consider. So we're not even giving it a name. So in this class, when we're doing a triple integral over some solid region D, we're just always going to assume that it's of this form. Okay, what form is that? It's kind of the analog of being vertically simple for a planar region R. So what is this, what type of region is this? Maybe I'll draw a picture here. So what type of region is this? The type of region we're going to concern ourselves with has an upper part that is the graph of some function. We'll call this upper function big F sub 2 of xy. So the top of this region is the graph of a function of two variables. The bottom of this region is also the graph of a function of two variables. We'll call this bottom function big F sub 1 of xy. Okay. And then I'm filling in the lateral sides, right? I'm like kind of filling in here. And how am I filling in? Well, the way that I'm saying that this solid region D exists is that it's got a top function and a bottom function. That's the top and the bottom. Okay, and I define this region D to be the solid region in space bounded above by the top function, below by the bottom function, all over some region R in the plane, or in the xy plane sitting in space. There's my x-axis, my y-axis, and my z-axis. So this is the type of region that I'm interested in. Okay. Now, this region R is itself either vertically or horizontally simple. Okay, where R is vertically, horizontally simple, and I'm going to put an asterisk here, or otherwise doable. Okay, so that's what my asterisk means. What I mean by that is this R is not necessarily vertically or horizontally simple, but it is the type of region R that is a type of region that we've dealt with in the first couple sections. Okay. All right. Now I should warn you before I go on, if you're looking at the textbook sections, then technically we just went from 14.2 to 14.4. This is 14.4 in the textbook. So the reason we skipped 14.3 is 14.3 deals with surface area. We are going to do surface area, but we're not going to do it the way that 14.3 does it because it's more convenient for us to just bundle it with what we're going to be doing at the end of the chapter. So 14.9 deals with parametric surfaces, and that is required to do all the chapter 15 stuff that we're going to be doing. And that gives you a much easier way of dealing with surface area anyway, so we're just going to wait to do surface area until then. So we're not really skipping 14.3, but in terms of chronological order, we are skipping it. So 14.1 is defining double integral, 14.2 is polar coordinates, 14.3 surface area, we're going to skip that. 14.4 is triple integral, so this is 14.4 material. Okay, and so how can I actually label this region algebraically? So similar to, well, there's a couple of cases that I'll go over here in a second. But you might have a couple of questions, namely, if I'm doing this, and I'm doing this as an analog to what I did here, this thing, this double integral computed a volume of a solid region that sat over this region R. Here, the region we're integrating over is a solid region. So what is this computing, right? In fact, if we're keeping the analog here, if this was dA, where A was an area we were integrating over, that's the idea here, we're integrating over a volume here, so it makes sense that we should call this dV, okay, fitting this pattern here. But if this thing computes a volume, right, so a single integral computes an area, right, that's Calc 1 and Calc 2 stuff. A double integral computes a volume. What's a triple integral compute? Well, it computes like a hypervolume, right? This is like a hypervolume. It is the hypervolume of the hyperregion in four-dimensional space that sits above, right, in a fourth dimension, this three-dimensional solid D. So there's a fourth dimension. I can't draw it here, right? So we're no good, but you can imagine there's a missing dimension here, right? So there's a missing dimension that is above, right? We'll call that missing dimension W, right? So we have X, Y, Z, and W. So in the W direction, right, sitting above this solid region, this solid 3D region D, there's the graph of f of x, y, z. It's a hypergraph, right? It's a four-dimensional graph. That hyperregion has a hypervolume. This triple integral computes it. Okay, but maybe you find that extremely unsatisfying. Okay, maybe you're like, I don't believe in hypervolume. Right, well, that's okay because hypervolume believes in you. Okay, but if you don't like the idea of hypervolume, there is something else that I can maybe sway you with, which is say we have some kind of solid region D. So here's a solid region in space D. Suppose that we have a function describing the distribution of mass of this solid region D. So now we're thinking of like a physical, actual, solid region, right? Let's say that we have a mass density function, right? That is describing the distribution of mass here of this object. Okay, and we'll call our mass density function, we'll call it like delta of xyz. This is the mass density function of D. Okay. All right. Well, if this delta is the mass density function of D, then it turns out that if I define this triple integral over D of this mass density function, what I get from this is actually the mass of D. Okay. Another example. So this isn't done at this point in the textbook. It's actually done at the end of this section. But I figured I'd go ahead and introduce it now because it can help with some of the intuition for what this is. Say that rho of xyz is a charge density function. So a similar role of the mass density function. It's describing distribution of charge on the region D. Then the triple integral over D of this rho function is Q, and Q is the total charge. So this is the total charge of D. Okay. All right. So this is kind of a more, this is something a little bit more concrete than me talking about hypervolume. But I do want you to know that the hypervolume interpretation is also perfectly fine. Okay. And we'll see after we define triple integrals. You'll see how the pattern goes. Then you can do quadruple integrals if you want to, or quintuple integrals. Those aren't actually done, and after Calc 3, whenever you're doing an integral over a region that is higher dimensional than 3, you just write a single integral sign because no one wants to write 10 integral signs, right? When you're integrating over some 10-dimensional region. Okay, and so that region D, let's see here. So we've got our region D. How can I describe this region? So let's say that R is vertically simple, right? So let's say R is vertically simple. Now I know what this means, right? If R is vertically simple. So if R is vertically simple, that means I can write that R is a region where the y values are bounded between two functions. We'll call them, say, g sub 1 of x and g sub 2 of x. And x is on some interval a to b, right? And if R is horizontally simple, then we use the notation that R is a region where x is bounded by left and right function. We'll say h sub 1 of y and h sub 2 of y, right, on left and right respectively. And y is bounded between, say, c and d. Okay. Now, for each of these, how would we label our region D? So for the first one, we would say that our region D is the region where Z is bounded between, recall our definition here, let's go back up here. Z, the height, is bounded between two functions of two variables, x and y, so big F sub 1 and big F sub 2. Oh, I'm not down far enough. So big F sub 1 and big F sub 2. And so D is the solid region such that the Z is bounded between big F sub 1 of xy and big F sub 2 of xy. And if R is vertically simple, right, then we would say that y is bounded between two functions g sub 1 of x and g sub 2 of x, and x is bounded between a and b. If R is horizontally simple, we would say that the z restrictions don't change, right? So the z height is bounded between two functions, big F sub 1 of xy and big F sub 2 of xy. And x is bounded between the functions h sub 1 of y and h sub 2 of y. And y is bounded between c and d. Now you see the pattern, right? So D is a three-dimensional region. So Z is bounded between two functions of two variables. Y is bounded between two functions of one variable. X is bounded between two constants. Again, over here, when R is horizontally simple, Z hasn't changed. It's bounded between two functions of two variables. X is bounded between two functions of one variable. Y is bounded between two constants. Okay. Now, in each case, how do we define the triple integral over D? So let's label this case 1, and we'll label this case 2. So in case 1, what is my triple integral over my region D of a function f of x, y, z, dv? How do I do this? So this is defined to be, now this is a little bit different than how the textbook does it. The textbook actually goes through the derivation of doing this in the same way you would do Riemann sums. I'm not going to go through any of that. So technically that's the definition. You can define this in an analogous way that you use Riemann sums to define both single and double integrals. I'm actually just defining this to be this thing that we're going to compute. It doesn't matter. This works out the same way. So this triple integral is the integral. So in the first case, really what it is it's the double integral over R of the integral from big F sub 1 of xy to big F sub 2 of xy of f of xyz dz dA. Okay. So really you're doing the double integral over R of this thing, which is the single integral with respect to z, where my limits of integration are these first two functions of two variables. Okay. And so if in this case, when R is vertically simple, I can write this out further. Well, this is the integral from a to b, the integral from g sub 1 of x to g sub 2 of x, the integral from big F sub 1 of xy to big F sub 2 of xy, little f of xyz, dz, dy, dx. Right. So in the second case, right, the idea is I now have a region that's horizontally simple. I'm going to skip this intermediate step, but this is really what it is. It's a double integral over R of this integral. So the z integral always comes first in this case, right? And so in the case where I have a horizontally simple region, my triple integral over D of little f of xyz dv is equal to the integral from c to d the integral from h sub 1 of y to h sub 2 of y, the integral from big F sub 1 of xy to big F sub 2 of xy of little f of xyz, dz dx dy, right? Okay. Now, when we do a couple of these, you're going to see exactly what it is that happens, although you can probably already tell what it is that's going on, right? The inner integral has limits of integration that are functions of two variables. The middle integral has has limits of integration that are functions of one variable. And the outer integral has limits of integration that are just constants. What does this mean? You start out with an integrand that is a function of three variables. You integrate with respect to z. You evaluate in z. That algebraically, that results in an expression that depends only on x and y, right? So one of your variables goes away here, right? Z goes away. And so you have an expression here that only depends on x and y, and now you're doing a double integral. So now you integrate with respect to y in this case. At the end of that, you evaluate in y, plugging in functions of x here, which means that the resulting expression you get is going to entirely depend on a single variable, x, which is good because the last thing you have to do is compute an integral with respect to x. And then you evaluate in constants, you get a number out of this. So just like with double integrals, you're always going to get some real number out of this process. Okay, so let's do a similar type example like we first did with double integrals, and let's pick kind of the absolute simplest thing that we can integrate over. So when we did double integrals, our first example was integrating over region R that was a rectangle, because a rectangle was kind of the simplest thing that we could integrate over, right? It's kind of the simplest region. What is the analog of a rectangle in space? Well, it's a parallelepiped, right? It's like a rectangular-based prism. So let's do that. So first example we'll do. So let R be the rectangular region bounded. So there's a rectangular region in the xy plane bounded by the lines x is equal to 2, x is equal to 5/2, y is equal to 0, and y is equal to pi. And let D be the solid region. Let's just say it's the parallelepiped. So let it be the parallelepiped. Oh, there we go. So let it be the parallelepiped between the planes z equals 0 and z equals 2 on R. Okay. So we have a rectangular region R. We have the plane z equals 0, that's the xy plane, and z equals 2 is the plane at z equals 2. But just over R, that forms this rectangular prism in space. Okay, so once we've nailed down what D is, then what I want to do is evaluate the triple integral over D of zx sine of xy dv. Now, here's a great time to go over advice that I always give when we talk about these things. So, for very few of these problems, do you actually need to visualize what it is that's going on? So a lot of students in Calc 3 stuff will complain that they can't see what's happening, they can't visualize what's going on, and that's like their main kind of obstruction to seeing to understanding what's happening. And the good news is that you really don't need to visualize almost anything here. So I'm going to draw this region D in a little picture over here, but it's not needed at all. Now, if you're not going to be able to visualize them, then you have to make up for that in being careful with the algebra that you're doing. Okay, so there are a few problems that, of course, are made much easier by visualization, and there are a couple of problems where you kind of have to visualize what's going on, but most of that stuff doesn't actually come till chapter 15. So for this stuff, to compute these triple integrals, for the most part, you don't need to visualize anything. It can be more satisfying and it can help, but you basically don't need to visualize anything. You can just well, yeah, of course, you can't see 4D, but I mean, I'm talking about even the three-dimensional regions that you're integrating over. So long as you can figure out what R is, you don't need to actually be able to visualize it. And many times you can figure out what R is purely algebraically. You don't need to draw a picture. But let's draw a picture anyway in this case. So here's x-axis, y-axis, z-axis. So we have a rectangular region in the xy plane, bounded by the lines x equals 2. That's a vertical line in the xy plane. So here's x equals 2. Right? So here's x equals 2. That's a line that looks like this, parallel to the y-axis. And then we have x is equal to 5/2. So, okay, this isn't going to be to scale, but this is just going to make our picture look sensible. So here's going to be x is equal to 5/2, so that's another line here. Okay, y equals 0, that's just the x-axis, so we've taken care of that. Y equals pi, well, that's a line, maybe there is where it is, right? So here's y is equal to pi. And this region D is the parallelepiped between the planes z equals 0 and z equals 2 on R. So here's our R, right? So I found my R here. I'm shading it now. So there's R. Okay, and D is the region above, or that this R is the base of D, right? It's the bottom. It's the z equals 0 part. So z equals 2 is a plane that is, at height 2 above R. So if I'm drawing what this thing looks like, here's like the front face of it. Here's the back face. Alright, so it looks something like this. Okay, there's my D. Okay, now remember, this D is not the thing we're computing the volume of. This D is the region we're integrating over. Now, this is purely for, your consumption. We didn't need to draw this at all, and you're about to see why we didn't need to draw this. This is a very simple region D. So describing this region, in fact, is very easy. Describing this in terms of whether, so first of all, R is a rectangle, so it is simple. It's both vertically simple and horizontally simple. So I can easily describe this region D. Z is bounded below by 0, above by 2. And I can go yx here or xy, right? I can treat it as horizontally simple or vertically simple. I'm going to treat it as a vertically simple region. So y is between 0 and pi. And x is between 2 and 5/2. So this region D, every single variable here is bounded between two constants. So this is as simple as it gets for triple integrals. Okay. All right, and so rewriting this another way, to do this integral, I need to compute the integral from 2 to 5/2, the integral from 0 to pi, the integral from 0 to 2 of zx sine of xy dv. Okay, so that's what I'm computing. So let me write that on a new sheet so I can do a bunch of work here. Okay. All right, so the integral that I'm trying to compute here is the integral from 2 to 5/2, the integral from 0 to pi, the integral from 0 to 2 of zx sine of xy I wrote dv before, but I actually already know what these things are. So dz, dy, dx. Now, the dz is always first in these kinds of integrals. Whether I do y or x first depends on whether or not I've written my region R as vertically or horizontally simple. In this case, R is simple, so I could do it either way. Sometimes your region R is only one, right? It's only horizontally or it's only vertically simple, so you'd be forced into a particular order. Okay. So we do this just like we did for double integrals. So when I do the integral with respect to z, I treat both y and x as constants. Okay, and so everything that shows up here is a constant except the z. So with respect to z, I'm integrating z times a big constant dz, right? So this is the integral from 2 to 5/2, the integral from 0 to pi. And this inner integral with respect to z is 1/2 z squared times x times sine of xy evaluated from 0 to 2 dy dx. Okay. All right. Let's do this evaluation. So evaluating at 0 is a polynomial thing. There's a z in every term, so plugging in 0 gives me 0 here, so only the 2 term matters. What do I get? I have 1/2 times 2 squared, so it's 1/2 times 4, so that's 2. So I'll pull the 2 out. So this is 2 times the integral from 2 to 5/2, integral from 0 to pi of, so this z is going away. And what I should have at this stage is an expression that that depends on at most 2 variables, right? So I have x sine of xy dy dx. Okay. Now I'm integrating with respect to y. Well, I'm thinking of this, so can I do this? I have this x here that's a constant. That's actually nice because it's exactly the constant that I need in order to do this integration, right? So I'm thinking of this, doing this integration using substitution. So treating that here, right? If I was thinking about this as u sub, right, where I'm only doing this integral with respect to y. So if u is xy, then du with respect to y is x, right? And there it is. So I actually have this perfectly. So this becomes, what's the integral of sine of blah, right? It's minus cosine, right? So this is minus 2 times the integral from 2 to 5/2 of cosine of xy evaluated from 0 to pi dx. Okay. And so what do I get here? So I get minus 2 times the integral from 2 to 5/2 of cosine of pi x minus, oh, I don't know why I wrote parentheses there, minus cosine of 0 times x, so 0 here, dx. Okay, so this is cosine 0 is 1, so this is cosine pi x here. So if I distribute this, this is the integral from 2 to 5/2, if you like, of 2 minus 2 cosine pi x dx. Okay. All right, so I can do this term by term then. So the integral of 2 dx is 2x. The integral of minus 2 cosine pi x is, so the integral of cosine pi x is 1 over pi sine pi x. So this is minus 2 over pi to compensate using u sub. So this is 2 over pi sine of pi x here, and I'm evaluating this entire expression, right, is evaluated from 2 to 5/2. Okay, so let's plug this in, plugging in 5/2 first. So this is 2 times 5/2 minus 2 over pi times sine of 5 pi over 2. Okay, that's 1, so that's not too bad. And then this, from that, I subtract 2 times 2 minus 2 over pi sine of 2 pi. Okay, so let's be careful here. Sine of 2 pi is 0, so that's cool. This is 1. This is 2 times 5 halves is 5. And this is 4. So I have 5 minus 4 minus 2 over pi, so that's 1 minus 2 over pi. And that's as simple as we can make that look, so that's that. Okay. What about the x? Let's see. Where did that come? Where did that question? Was that question about this? It's what happened here. I'm assuming that that's what the question is. What about the x? This is, remember, at this stage you're integrating with respect to y, so you're holding x as a constant. So if you do u sub here, right? U is xy. What is du? Keeping in mind that this du we're taking is with respect to y, meaning it's kind of like a partial du here, right? Du in this case is x is a constant, so it's x dy, right? So I have x dy here. So it gets absorbed. If I rewrite this as an integral of blah blah sine u du, this is what I have going on, right? So this x gets absorbed into making du to do substitution, yeah. And that's something that you're gonna have to do with a lot of these, okay? So you're gonna have to do that with a lot of these, and you see how cumbersome this is to do, what is u sub. If you actually write it out, you have to keep track of the fact that this d is actually it's just with respect to y. So it's kind of like a partial differential operator. So because of that, it's typically better to try your best to do it in your head. So that you don't totally, have too much stuff going on here and confuse yourself with how this works. So it's best to try to do it in your head as much as you can, so that the computation doesn't get too messy. But of course, take your time when you're doing this and work through it like this. This is going to come up a lot, though. Exactly, things like this are going to crop up all the time in these. Okay. All right. So I only have a couple more minutes, so it's probably not enough to do an entire other example. But maybe I can set one up, which is the next one I want to do. Yeah, let's do, I'm just going to go straight to the next example. We'll at least set it up, and then we'll do it on Monday. So here's the next example. So let R be the triangular region in the xy plane between the graphs y equals x and y equals 1 for x between 0 and 1. And let D be the solid region between the graphs of the surfaces z equals -2, which is just a plane at the -2 height, and z equals 1 minus x squared for ordered pairs in R. Z equals 1 minus x squared, that's a parabolic sheet. So remember, if you go to files on Elms forever ago, I posted a list of some of the basic graphs. If you haven't had a look at that, it's at the very beginning of chapter 13 stuff. I posted that. You can have a look. This is a parabolic sheet. And so envisioning this is a little bit hard, but there's no need to. I don't have to. As long as I pay attention to what's going on algebraically, I'm fine. So if you want to see a picture of this, this is on page 929 in the book. So you want to see what a picture of this looks like, this is on page 929. Also, once you're more comfortable with MATLAB, you could use MATLAB to generate a picture of this thing if you wanted to. But anyway, how can I set this up? So I've got my z bounds, I have my x bounds, I've got my y bounds. So if I want to evaluate the triple integral over d of x plus 1 dv, how does that go? This would be the integral from 0 to 1. The integral from, well, y equals x and y equals 1. Which one is above which? Actually, y equals x is the lower one, right? So this is on that interval. From 0 to 1, y equals x is the lower one. Okay, so this is the integral from x to 1. The integral from minus 2 to 1 minus x squared of x plus 1 dz, dy, dx. Again, the region in question is simple, so we could have done this, we could have done the y and the x in any order we wanted to, but we just treated it as a vertically simple region again. Okay, so next time, yeah, so the question in chat is whether or not you can do it in your head for the exam. The substitution like that you can do that step, but you should still have you see that there was no shortcut here. If I don't write this, right? If I don't write this at all, there's still no shortcut. I'm going through this at every single step. Once I have this, now I can do this integral. You can do this, right? But you still have to write out all this stuff. You can't skip from here to the evaluation stage, right? So every single integral you should do separately, and it should be very clear how you're doing it. Okay. So anyway, on Monday we will finish up triple integral in rectangular coordinates and start on doing triple integrals in other coordinate systems. Okay, and by the end of next week, we will start, maybe not on next Friday, but maybe the Monday after, we'll start on change of variables, and then we'll almost be done with chapter 14. So we'll be moving on to chapter 15 stuff, and it'll be almost time for your third exam in another couple of weeks. Okay. So anyway, that's the deal. We'll pick up here. I'll finish this example at the beginning of class on Monday. So like I said in chat, I'll post your homework sometime tonight or early tomorrow, and it'll be due next week, no sooner than Wednesday, and it'll cover up through triple integrals. So anyway, that's the deal. So I'll see you all on Monday.